we can officially open the seminar with the first introduction, a short introduction of our speaker. Lars studied physics and mathematics at the University of Hamburg and the University of Cambridge in the UK. He did his PhD at the University of Munich, and the topic is exactly what he is right now reporting on, the direct detection of the thorium isomer 229. And after completion of his PhD in 2017, he worked in Munich for a few years, and then last year he became a Humboldt Fellow at the JILA in Boulder. So this is a joint institute of the University of Colorado Boulder and the NIST. And the topic is about, of course, laser spectroscopy of the thorium-229 isomer. He got several awards. I don't want to list all this, but let's see, two of them are worth to mention here. The Röntgen Prize of the University of Gießen in 2018, and last year the Theodor Hensch Prize of the LMU of the University of Munich. So we are eager to listen to your talk. Please, Lars, thank you.
Thank you, Mustafa, for the kind introduction. And also I would like to thank the organizers for the invitation. It's my pleasure and a particular honor for me to present some of our work now here in the Quantum Seminar. So actually I have a minor correction to what Mustafa just said. So the direct detection of the thorium-229 isomer, this was like back in 2016, and there has been some other and more recent, very exciting progress in this topic. So for this reason, I will mainly leave out the work that I did during my PhD thesis back in Munich, but I would like to give more of an update on what happened within the past year, published since August or September 2019. So this is mostly an update on the most recent progress, which is quite exciting on this topic. So the topic is the nuclear optical clock development based on this very special thorium-229 isomeric state, which is intrinsically already exciting because it is the isomeric state of lowest excitation energy in the whole nuclear landscape. So this is what makes thorium-229 special, and in particular, what makes thorium-229 suitable for the development of a nuclear optical clock. So let me start with an outline of my presentation. So I'd like to start with thorium-229 for time measurement in general. And I would like to talk about optical atomic clocks in particular, because a nuclear clock is a very special case of an optical atomic clock. So I would like to introduce how optical atomic clocks are operational. If you have understood this, it's easy to understand how a nuclear optical clock will work. And then I would like to discuss how thorium-229 is important for the development of such a nuclear optical clock. So I have a relatively long introductory part. Then I would come to the central part of the talk, which is about the recent thorium-229 progress. And the main important thing is that within the past years, the thorium-229 energy has been constrained significantly improved. And this was done with 3 different methods. And I would like to introduce all 3 different methods now that have led to this significant progress in this field. And in the last section, I would like to discuss how this new knowledge can now be applied to actually develop a nuclear clock. So based on this new knowledge, we have made some significant progress into this direction, and this offers great new opportunities, which I would like to discuss in the end. So let me start with discussing how time is actually measured. So what time measurement needs is something that is changing periodically. So this could, for example, be a pendulum that swings in a harmonic way. And what you do then, you can count the oscillations of this pendulum and then say, okay, 1 hour has elapsed after my pendulum has been swinging around like so and so many times. And in the case of the pendulum, the frequency of this oscillation only depends on the acceleration of the Earth and the length of the pendulum, which is already quite good, because if you manage to develop pendulums that have always the same length, they will always swing with the same frequency everywhere on Earth. However, if you go to the moon, for example, then your pendulum will suddenly have a different frequency. So it's not quite worth to define the time standard or define the second based on the swing of the pendulum, because it's not everywhere on every place in the world or in the universe the same. However, still on Earth, you get a quite good standard with this, and this is why pendulums have been amazingly successful. So for 300 years, pendulums were the most used and most precise time standards. And the pendulum clocks that I show here is the short synchronum, which was the most accurate pendulum clocks that has ever been built. And the accuracy was quite stunning. So this was an accuracy of 1 second per year already, which is good considering this is like a macroscopic mechanical device. And it was also the first clock that was actually more accurate than the Earth's rotation itself. So you maybe know that until 1960, the second was defined based on the Earth's rotation. And this clock, although it was not measured with this clock at the time, but this clock was the first clock that actually was more accurate than the Earth's rotation itself, which is very very technologically advanced. So, but we all know that by today things have improved a lot, and today's best reported time accuracies are achieved by optical atomic clocks. And similar to the pendulum, also in this case, there is some harmonic motion required. So again, you have some oscillation, but this time, this is not a macroscopic device, which is doing mechanical motions. But in this time, in a simple pictorial understanding, it's your electron that swings around the nucleus of your atom. So this generates you the frequency, but now the frequency is a lot larger, whereas the pendulum swings like by about 1 swing per second or something. This electron oscillates like in the gigahertz range. So you have a lot more, or terahertz range even. So you have a lot higher frequencies, and this allows you to subdivide your second into much smaller fractions. And in this way, you significantly gain 1 by 1 in accuracy. And what I list here are some of the most accurate optical atomic clocks that are operational today. And you can see that they are all accurate by about 10 to the minus 18, which corresponds to 1 second of inaccuracy within 30 billion years, which is longer than the age of the universe. So you have a very stunning accuracy based on this optical atomic clocks. And the most accurate one is actually the aluminum single ion clock, which even has surpassed the 1 times 10 to the minus 18 accuracy range and is now approaching into the 10 to the minus 19 range here. This was published last year. The picture that I show here is the photograph of the optical atomic clock, which is closest to the place where I currently work. It's actually in the lab next door. So this is the strontium optical lattice clock that is operational at JILA in the group of Junyi. So now how does this actually work? So the principle of operation is that actually the atomic transition frequency is independent of space and time. So wherever you take your atom, you should always measure the same frequency. This is, of course, excluding general relativistic effects here, which start to hit into the game if you come to the 10 to the minus 18, 10 to the minus 19 range. But like on a first order approximation, your atomic transition frequency is independent of space and time, and all atoms of the same species, of course, are fundamentally identical. So it's not like a pendulum clock where you build one device and it has a particular frequency because the pendulum has a particular length, and then you build another device and this has a slightly different frequency, but the atoms are fundamentally identical. So you can use them even to define the second this way. So what you now want, the goal is to actually count the number of oscillations of your atomic transitions. And in a practical realization, the way you do is is you lock an ultra stable laser to an atomic transition so that your laser has the same frequency that you need to drive the transition. And as the frequency itself is independent of space and time, you know that also your laser will then have a frequency which is independent of space and time. So all you need to do is then to count the number or the frequency of the oscillations of your laser light. And this is done with a frequency comb. So by using an optical frequency comb, you can technically really count the number of oscillations of your atomic transition. And then you can say, okay, 1 second has elapsed after a certain number of oscillations of your laser light that has been blocked to this particular atomic transition. And this is a way you can define the second, you can measure time in general. And this is how it's done. So what you see here is your lasers that you use for the spectroscopy. The laser needs to be coupled to an ultra low noise cavity to narrow the line width. Then you stabilize your laser to the nuclear transition, or sorry, atomic transition in this case, via a feedback loop. And at the same time, you have a frequency comb that allows you via the beat nodes that you generate with your laser light to the frequency comb to really count the frequency of your light wave. So this brings me to the nuclear clock. The question is, can we potentially even do better? And the idea is here not to use an atomic shell transition, but instead to use a nuclear transition for laser stabilization. And again, an oscillation is involved here. And in my simple pictorial understanding, this is now not an electron that swings around the nucleus, but it's some nuclide, like the neutron, for example, that is oscillating in your nucleus itself. And again, this generates you some oscillator behaviors. This is, of course, an oversimplified picture, but just to give you the correspondence here. So what's the expected advantage in using a nuclear transition instead of an atomic shell transition for time measurement? And in a simple way, the idea is that the nucleus is like 5 orders of magnitude smaller than the atomic shell. So what you expect is you expect to have better performance because the nucleus is highly resilient against external influences because the nuclear magnetic moments or electric moments are much smaller than the one of the electronic shell. So you're simply significantly less influenced by external perturbing fields. And in this way, the estimated expected accuracy of a nuclear clock that could be approached is in the 10 to the minus 19 range, which corresponds to like 1 second in 300 billion years. So this is the abstract underlying idea of this concept. Now, there is not one single nuclear clock concept that could be built. So the most generally known is the single ion nuclear clock, where you say, okay, simply like for a single ion atomic clock, like the aluminum single ion clock, you trap a single thorium-229, in this case, thorium-229 ion in a Paul trap. Then you irradiate this ion, or the nucleus in particular, by laser spectroscopy. And now you have to find a way to probe that actually you are successfully exciting the nucleus. And the way to do is you use that the excited nuclear state has a different spin state of the ground state. So what happened is, due to the different spin states, your shell hyperfine structure changes. And this is something that you can potentially easily probe with a spectroscopy, by a spectroscopy of the shell, of the electronic shell. And then you measure the shell fluorescence photons. And this is a way you are able to generate a feedback in order to lock your laser system to the nuclear transition. So now there's one disadvantage of the single ion nuclear clock, namely you have just one single nucleus that you use for stabilizing your laser, and you would gain significant advantage if you would use more because your signal to background ratio would change. So there is the idea that you could use multiple ions instead. So you could imagine like having a chain in a linear Paul trap of like 100 ions. And this would help you significantly in stability, in signal to noise ratio of your clock. So in this way, you can faster make use of your high expected accuracy. But other than that, the underlying principle remains exactly the same. But there is a different idea. So The nucleus is expected to be largely unaffected by the electronic shell, and this would allow you to embed many nuclei, like a huge amount of nuclei, 10 to the order of 14 or something nuclei, into a crystal lattice environment. And this would, of course, gain drastically in signal to background ratio, however, on the cost of external perturbing influences, because here you can imagine your nucleus would be largely separated from all environmental surroundings, where in this case, you are sensitive to some temperature drifts and stuff like that. So for this reason, you will have high stability, but on the other hand, you will have lower accuracy of the clock. And there's a fourth way of making use of this nuclear transition for laser stabilization, and this is the so-called internal conversion nuclear clock. And what you use here, essentially you do the exactly same thing, but here in this case, you want to probe the successful excitation of your nuclear state via the detection of photons emitted in the isomeric decay, whereas here you make use of a different decay channel, which is the so-called internal conversion decay, where no electrons are emitted, but where instead no photons are emitted, but where instead electrons are emitted. And in this way, you can also stabilize your laser to the nuclear transition in a solid state environment. So there are two fundamental differences. These are ion-based, trap-based clocks, and these are solid state clocks that you could potentially build. So now we can compare those. And as I already mentioned, so the single ion and multiple ion clocks, the trap-based clocks, are separated a lot better from the environment. So you have an accuracy of 10 to the minus 19. Whereas the solid state clocks are only expected to achieve a 10 to the minus 16 accuracy, which is still sufficient for many applications. So for many applications, you don't need this super duper high accuracy of the clock, but 10 to the minus 16 would be sufficient for you. And in these cases, these solid state clocks would have advantage because they're much more robust and simple to develop, because you don't need to have a trap, you don't need to read out the hyperfine structure. So they are technologically a lot simpler, but less accurate. So now, if this is such a great thing, why don't we simply build such a clock? And so one central requirement is that you actually have to laser excite your nucleus. So direct nuclear laser excitation is the central requirement for a nuclear clock. And lasers are only available in the electron volt range energy spectrum. However, nuclear energy scales are typically like in the kilo electron volt to mega electron volt ranges. So there is little bit up to no overlap between the energy range of lasers and the energy range of nuclear transitions. And this is a big problem that hinders us from developing a large variety of different nuclear clocks, like we have the opportunity for atomic clocks, for example. But there is one exception, and of the total known number of more than 3,000 known isotopes and the total number of like more than 175,000 nuclear levels with almost 270,000 transitions, there is one and only one nuclear transition that is low enough in energy to allow for direct laser excitation. And this is this particular thorium-229M isomeric state. So this is the reason why like all nuclear clock development always circles around the thorium-229 metastable isomeric state, simply because it has such an exceptionally low energy, which is only 8.1 electron volts roughly, which corresponds to 152 nanometers in wavelengths. And this is really exceptionally small. In addition to that, the lifetime of the state is in the range of hours. Like the latest predicted value is 1.2 times 10 to the 4 seconds, and this makes the line width to be exceptionally small. So delta E over E, the relative line width, is in the range of 10 to the minus 20, which is of course an important feature. If you think that you want to stabilize your laser to this transition, you want to be very sensitive to the particular frequency. So you would want to immediately know if you are off resonance. And for this reason, it's important that you have a very high quality factor of your resonance. So this relative line width is an important factor. So this is a very suitable transition actually for the development of a nuclear clock. And here I show you an energy half-life diagram of all existing or all known metastable nuclear states. And here you can see the special position of thorium-229, which is down here. So usually the energy scale of nuclear excitations is like starts at 10 kilo electron volt and goes up to 10 mega electron volts. And then there is like 3 orders of magnitude nothing. And then suddenly there comes the thorium-229 metastable state, which is in a region where you have usual nuclear optical clocks, optical atomic clocks operational based on different transitions. So this particular state is located in a region where optical atomic clocks are in operation. So now there has been a very central challenge that has hindered the development of a nuclear clock based on thorium-229M within the past decade, I would say, or even 2 decades almost. And the reason is that for a long time, this thorium-229 energy was not sufficiently well constrained to allow for precision laser spectroscopy. And precision laser spectroscopy is actually what you want. So as long as you can't do this, you simply can't build the clock from that. However, since 2019, a total of 7 new energy values were published, and this has essentially solved this long-standing problem. So while previously we were just not knowing where to search for the nuclear transition during the excitation, we now have a pretty clear picture. And these are the last 7 values that were published of the energy of the metastable excited state. And the weighted mean of the past 8 values is 8.12 electron volts, which corresponds to 150.7 plus minus 2.1 nanometer. So we have now, for the first time, actually a pretty clear picture where the isomeric energy state is located. So this first value that is plotted here, this is back from 1994. Then there came a next one, which was dates back to 2005. And then 2 further values were published, one in 2007, one in 2009. And you can already see here that previously there has been a significant decrease in the energy. So people were pretty uncertain where the energy would actually be. While now we are having a pretty clear picture. Okay, we should look around 8.1 electron volt. And this is where it's worth starting to do laser spectroscopy. This brings me to the second part of my presentation, where I would like to discuss the different methods that were used within the past year to refine the thorium-229 energy value. And you can distinguish between 3 different methods, conceptual methods that were used. You have to think that laser spectroscopy is ruled out, right? Ideally, you would like to determine the isomeric energy value by doing high precision laser spectroscopy, and then everything is done. But if we could do this, we could also develop the nuclear clock. So this has so far not been possible. So for this reason, we are now searching for different methods that would allow us to measure the isomeric energy value. And one way is via higher lying nuclear states. So we have this thorium-229 metastable excited state lying here, but of course there are nuclear states of higher excitation energies. And some of these higher lying nuclear excited states may populate the metastable excited states and partly also populate the ground state. So you would expect that there are gamma rays emitted from these higher lying excited states. And if you are able to measure the energies of these gamma rays and then subtract the energies of these gamma rays from each other, you get exactly this difference of grounded excited states. So this is the method that has been investigated the most historically. So this so far has been, yeah, I would say even the most important way to infer energy values for the thorium-229 metastable state. So very recently, there has been a second method become available, which is to do a lambda excitation of the thorium-229 state. In this experiment, what was done is one higher excited nuclear level was populated from the thorium-229 ground state. So you need X-ray sources for that, right? So you need high energy gamma rays to do this excitation from the ground state. And this was done, and in this way it was possible to actually measure this higher energy level to very high accuracy, because as soon as you can excite it from the ground state with some X-ray source, you can measure the energy of this X-ray to very, very high accuracy, which allows you then to measure the energy of this higher excited state to very high accuracy. And this state decays to the ground state. And now you again rely on measuring the energy of a gamma ray that is emitted in this process. So by subtracting these two energies, you measure again the energy of the metastable excited state. And there's a third method, which I call direct decay. So what you do here, you in some way populate the excited state. This is, in this case here, the metastable state. And this decays to the ground state under emission of either a photon or an electron. And if you now measure these gamma or photon or electron that is emitted here, in this way you can, of course, also try to infer a value for the isomeric energy, which is probably the most direct one, which was investigated mainly in my former group in Munich by Peter Tirov. So I would like to quickly now discuss each individual method on its own. So method one is to probe the high energy gamma rays. So there are a couple of high excited states in thorium-229 available, and they are typically populated in the alpha decay of uranium-233. So you have a natural way to populate the thorium-229 excited states, because uranium-233 decays by alpha decay with 160,000 years half-life, and then during this decay, higher excited states of the nucleus are populated in a natural way. So you get this for free if you have a uranium-233 sample. So here is your uranium-233 sample, and one particular very important excited state that you need is the second excited nuclear state of thorium-229, which has an energy of 29 kiloelectron volts. And this 29 keV state partly populates to the ground state with a branching ratio of about 10%, and partly populates, or mainly even populates, the thorium-229 excited state. So if you measure this 29 keV gamma ray that is emitted in the decay of the state, you will see that this is actually not a single ray, but it is a doublet, because fraction of it is going to the ground state, fraction is going to the excited state. And if you are able to resolve this doublet, you would be able to infer the isomeric energy value to very high accuracy. Now, a clear resolution of this doublet has not been achieved, because you need gamma ray detectors of extraordinary high accuracy, high resolution, spectral resolution, to be able to distinguish between this very small, think about it, it's 29 keV, but you want to measure like 10 eV difference here. So you need extremely high resolving gamma ray detectors to spectroscopically resolve this. But in 2020, actually, for the first time, a measurement was published where it was possible to not resolve these, but to actually make the asymmetry of this doublet visible. So here you can see that this is a measured line, and it has clearly an asymmetric shape, which is due to this doublet that you are actually measuring. And based on this asymmetry, already it is possible to infer some value of the isomeric energy. And by a best fit, the energy that was obtained here is 7.84 plus minus 0.29 electron volt. And this was published in the paper of Thomas Sikorsky et al. Just recently in 2020. So this is very exciting news. On the other hand, it doesn't really entirely solve this problem, because you would like to still push the limits further to actually clearly resolve these two lines. But this is hard. It would require like a factor of 3 more spectroscopic resolution. but maybe there is hope that within the next couple of years this might be achieved. So this offers great prospects for high precision measurement. So this brings me to a different way, but by the same method to investigate the energy. So as long as this 29 keV doublet was not fully resolved, you can investigate more complex schemes. And this is what has historically been done. So for example, the uranium-233 decays also to some other higher lying excited state. And one important one is the 72 keV state, which has one cascade to the isomeric state and has one cascade to the nuclear ground state. And now if you subtract these two cascades from each other, you can infer the isomeric energy value again. And there is one interesting coincidence, namely that one of these gamma rays of the one cascade has a 42 keV, and this one is very close by. It's only 200 electron volts apart from this gamma ray, which is very close by in terms of the nuclear energy scale. So for this reason, you can measure this difference and similar this difference to extraordinary high accuracy for nuclear spectroscopy terms, because they are only 200 electron volt apart. And if you now subtract these two from each other, in this case, you get the isomeric energy value, and have just by this coincidence that they are so close by, you have a very accurate measurement of the isomeric energy. And this is what was historically investigated the most. It was first investigated in 2007. Back that time, it was for the first time possible to actually resolve these two lines, because previously gamma ray spectroscopy was not developed to high precision to actually resolve these two lines. So this did show up previously just as a doublet. But back in 2007, for the first time, it was possible to resolve this doublet. And then this allowed for high precision measurement of the isomeric energy. And in 2009, this was inferred to be 7.8 electron volts, which was for 10 years until 2019, the most precise energy value. And now the same scheme was re-investigated by Sikorsky et al., however, with 3 times improved energy resolution, and the new best value obtained by the same method is this 8.1 plus minus 0.17 electron volts. So this brings me to method 2, which is a lambda excitation of the thorium-229 metastable state. Again, the 29 keV state plays the important role here. So what was done, the second excited state of thorium-229 was populated from the nuclear ground state. And for that purpose, you had to do synchrotron irradiation, which was done at the Spring 8 facility at Riken in Japan. So they were able to excite the 29 keV state, second excited state, from the ground state. And then the resonance is observed, which you can see here, via X-rays that are emitted delayed during the internal conversion de-excitation of the isomeric state. So what they did, they had pulsed synchrotron radiation, 40 picosecond pulse duration. It needs to be that short because the lifetime of this excited state is only 80 picoseconds actually. So you need very short pulses. And then you observe the decay shortly after each pulse on some certain background. And if you do this, you can be sure that you have actually hit the nuclear resonance. And then you determine the energy of your X-ray beam to extremely high accuracy. So in this case, the line energy was measured to be 29,189.93 plus minus 0.07 electron volts. So this is now a very high accurate measurement of this 29 keV state. But in order to extract the thorium-229 isomeric energy from that, you have to combine this with the gamma decay measurement, which can only be done in the ordinary way. So for this reason, the uncertainty that you actually achieve by this method is dominated by the uncertainty that you have available to measure this 29 keV gamma decay. And this was done in 2 different papers. Like the first one by Yamaguchi et al. Obtains a value of 8.3 plus minus 0.92 electron volts, and the second one 7.8 plus minus 0.8 electron volts. So you can already see here that the uncertainty is a lot larger. However, still this is an important consistency check. So this is still of some value to see, okay, everything, all measurements are consistent in this case. So this brings me to the third method, which was the one investigated by our group back in Munich, the direct observation of the isomeric decay. And here we have to distinguish that the isomeric decay to the nuclear ground state can proceed in 2 ways. The first way is simply the ordinary gamma decay, where the metastable state decays to the ground state, emitting a photon, which you can then measure. The second way is the internal conversion decay, where what's happening is the isomeric decay decays down to the ground state, and the energy is transferred to the nucleus via a virtual photon, to the shell via a virtual photon. And then what's happening is an electron is kicked out of the electronic shell. So the energy is transferred from the nucleus to the electronic shell, and the energy is released by the emission of an electron. And now it's important for low energy nuclear excited states, internal conversion is always a dominant decay channel if it's energetically allowed. So for all low energy nuclear excited states, you would first expect to see internal conversion. And in the particular case of thorium-229, the internal conversion decay is favored compared to the gamma decay by 9 orders of magnitude. So you get a factor of 1 billion higher internal conversion decay rates compared to gamma decay rates. However, as the thorium-229 metastable state is so low in energy, this is energetically allowed only for neutral thorium-229M. Already, if you go to single charged thorium-229 ions, you don't have enough energy available in the nuclear de-excitation to really release 1 electron from the shell. So in this case, the internal conversion decay channel gets energetically suppressed. However, as long as it's energetically allowed, it's favorable by 9 orders of magnitude. And this reduces the lifetime by the same order of magnitude. So you get 10 microseconds lifetime as opposed to the 10 to 4 seconds lifetime that you would expect in the pure radiative decay. So it's important to say that only the internal conversion decay channel of the metastable excited state has been experimentally observed. The gamma decay of this metastable state has not been experimentally observed to the current point. The reason is, okay, you can imagine if you suppress the internal conversion decay channel, which you need to do in order to have any chance to detect photons being emitted here, you need to go to thorium-229 ions. But usually thorium-229 ions are having a lower density because you have the Coulomb repelling. So in a Paul trap, for example, you cannot keep thorium-229 ions in the same density as you could keep neutral thorium-229M. So you are working with lower amounts of ions. And for this reason, it's statistically harder to observe this decay. The only way to make use of this is by going into a crystal lattice where thorium-229 is already in the 4+ charge state, for example, in a crystal lattice. But in this case, you still have the electronic environment there, and there might be some non-radiative decay channels. However, this is a way that is currently investigated, and there might be the chance to actually observe these photons in a crystal lattice environment. However, so far it has not yet been experimentally successful. So now what we did that time is we observed the decay via the emission of photons. And for that purpose, we were populating thorium-229M in the alpha decay. In this decay channel, about 2% of the thorium-229 ends up in the isomeric state. And we then generated a thermalized thorium-229 ion beam in the 2+ or 3+ charge state from that. So in the thorium-229 2+ or 3+ ion beam, you remember the internal conversion is energetically suppressed. So you get a long lifetime. So your isomer potentially lives up to hours in the thermalized ion beam. However, you want now to see a detection. So you have to neutralize your thorium-229 ions, which was done in a graphene foil. This triggers the internal conversion decay, and what was done then was spectroscopy of the kinetic energy of the IC electrons. And this is the IC spectroscopy curve here. And then you can see from the scheme already, so the energy of the nucleus corresponds to the ionization potential that you need to release one electron of the shell into the vacuum, plus the kinetic energy of your electron. And if you add these up, you can obtain an energy value which was measured to be 8.28 plus minus 0.17 electron volt. And this measurement was covered by Nature at the time, together with the method 2, the lambda excitation. So both methods appeared in the same journal that time. So this brings me to the last part of my talk already. So now, having this new knowledge at hand, what do we learn from that? And I would like to argue here that this offers great new opportunities for narrowband laser spectroscopy of thorium-229M, because previously it was simply unclear which technology would be most suitable, like CW laser that you would like ideally to do, or direct frequency comb spectroscopy. In addition to that, also long scanning times with multiple types of lasers would have been required in order to search for the nuclear transition. But with this new knowledge now, we know that CW laser spectroscopy, at least based on existing technology, is ruled out simply because there is no CW laser today available at the isomeric energy value of 150 nanometer. So direct frequency comb spectroscopy is today the only option. In addition to that, we now know that just by coincidence, the 7th harmonic energy of an ytterbium-doped fiber frequency comb exactly matches the expected nuclear energy. So an ytterbium-doped fiber frequency comb is typically located around 1070 nanometers. If you divide this by 7, you obtain 152.8 nanometers. And the weighted mean of the energy corresponds to 152.7. So we are just by coincidence almost exactly matching the nuclear transition energy with the energy of the 7th harmonic of the ytterbium-doped fiber frequency comb. So this offers great opportunities because we now know, okay, it's worth searching for the nuclear excitation with a direct frequency comb. And the question that I would like to raise is, can we immediately use this information to develop a nuclear clock? And for this reason, I would like to remember you on the different nuclear clock concepts that we were discussing in the very beginning. So we remember we have these 2 types of trap-based nuclear clocks, single ion or nuclear or multiple ion nuclear clock. And I would like to argue that these clocks are probably like the ultimate goal because they achieve the highest accuracy, but they are also the clocks that are experimentally the most demanding because you have to trap thorium-229 ions, either a single or multiple ones in a Paul trap. You have to laser cool them. Ideally, you would want to do direct laser cooling of thorium-3+, which has been experimentally done. Just a second. Get some power prompts here. So, which has been experimentally done, but which is extraordinary demanding to do direct laser cooling of thorium-3+. Then you have to read out the hyperfine structure of the states in order to check for the nuclear spin state to determine whether you are actually successfully excited the state. And in addition, you are doing all this with very low statistics because you have only like one or maybe a couple, like 100 of ions available. So I would like to argue that this is a very complicated concept, although being the ultimate goal. Now you can say, okay, we want to do something which is simpler, which is developing solid state clocks, like the crystal lattice clock or the internal conversion clock. Here, this is simpler, conceptually simpler, because you are just working with a lot more nuclei. So by definition, you are working with a 10 to the 14 or 10 to the 13 nuclei that you can laser excite in parallel. So you have a lot higher density of nuclei that you can work with, which makes it conceptually easier. So the difference between these two clocks is that here you rely on the observation of photons that are emitted directly in the isomeric decay. And no one has so far ever observed these photons. So this is very challenging, probably because there are strong non-radiative decay channels that are competing the radiative decay in a solid state environment and that have so far not been successfully suppressed. So for example, it might be possible that simply so far the internal conversion decay channel was just not successfully suppressed, but there are also other decay channels like electronic bridge decays where the nucleus couples to the electronic shell without the emission of an electron. So this is very demanding simply because it's very hard, obviously, to suppress the non-radiative decay channels of the isomeric state. So this is why I put a red stamp on here, which requires the observation of photons, which has not been successful so far. But this last part, I would argue that the internal conversion nuclear clock is probably the simplest approach because we have all knowledge that we need for this type of clock. So it's relatively simple because you have a large amount of nuclei that you are irradiating in parallel. So you have a large statistics available. And on the other hand, the internal conversion decay channel has already been successfully observed, and we know all parameters that are involved in this decay. So we know the lifetime, we know the energy, we know the line width that we are expecting in this decay because we have observed the lifetime. So if I would have to bet, I would expect that this internal conversion nuclear clock will be the first nuclear clock that will be built because of this reasons. So for this reason, I would like to argue that one should start with a low-hanging fruit and start with the development of an internal conversion nuclear clock first. And this is what we are currently investigating here at JILA. So this is essentially the experiment I'm working on right now. And what we are doing is we want to irradiate a thorium metal or thorium oxide layer, which is sitting on this metal substrate here, a very thin one, like 10 nanometer thick thorium oxide layer sitting on this metal substrate. And we want to irradiate this with 100 microsecond laser pulses. So now you can calculate if we cover part of the target with a pinhole of 300 micrometer diameter, we would irradiate like 10 to the 13 nuclei in parallel on the surface. And if we now assume that we have 1 nanowatt of laser power, which is roughly realistic if you consider that you use one individual comb tooth of a frequency comb in the vacuum ultraviolet for laser spectroscopy, then you can calculate via the optical Bloch equations how many nuclei you are exciting per laser pulse. And this is a very small fraction considering that you're irradiating 10 to the 13 nuclei. However, still it is a measurable number. So you're expecting to excite about 6 nuclei per laser pulse by solving the optical Bloch equation. And this, what you see here, is just the number of excited nuclei after over time after the start of the irradiation for a maximum time of 100 microseconds. So this is the concept. And what you want to do then, you want to detect the de-excitation of this nuclei, and we know that these will decay with about 10 microsecond lifetime under internal conversion via the emission of an electron. So the idea would then to detect the internal conversion electrons with an MCP detector after the laser pulse. So we switch off our laser pulse with, for example, a chopper wheel. We switch the light off, and then we start to observe the internal conversion decay with a decay lifetime of 10 microseconds. Now we can put some assumptions here, like let's assume we are detecting internal conversion electrons in a 5 microsecond time window right after each laser pulse. Let's assume we have 10% extraction efficiency, which is a value which is estimated based on some calculations. And let's assume 50% detection efficiency of the MCP detector. This will lead to 0.1 detected electrons per laser pulse, which doesn't sound much, but we have to consider that we have 100 microsecond pulses. So we could irradiate our target with 5 kilohertz repetition rate, roughly. And if you multiply this with 5,000 laser pulses, then you have already a significant amount of electrons from the internal conversion that you can potentially detect. Now we need to compare this with electrons that are continuously emitted from the target due to the intrinsic thorium-229 radioactivity. So thorium-229 is radioactive with a lifetime of about 7,900 years. And it's an alpha emitter. There's some other daughters that are growing up intrinsically in this target substrate. Based on measurements that we were recently doing, we expect to have 0.0015 background electrons in the same 5 microsecond detection window, which are originating from the thorium-229 intrinsic radioactivity. And this leads us to a signal to background ratio, which is expected to be roughly 60:1. So there is a reasonable chance to detect some internal conversion decay electrons despite this radioactive background of the target. Which brings me to the laser system that we are planning to use, which is the more complex part. So the target is very simple, but we need the laser system to irradiate this target. And for this reason, for this purpose, we want to use the 7th harmonic generated in a helium-xenon gas mixture from an yttrium-doped fiber frequency comb. So what you see here is the yttrium-doped fiber frequency comb. And this is locked to some optical lattice clock, which is sitting in the neighboring lab. So we can use the laser, which is ultra narrowband and absolutely referenced to the strontium lattice. So we use this laser, the strontium clock laser at 698 nanometers to lock our comb to the spectroscopy laser. In addition, we have an F-2F interferometer for locking FCO, so we can lock F-beat and FCO. In this way, we have an entirely locked infrared frequency comb. We amplify this comb by coupling to a fiber stretcher, preamplifier, power amplifier, and a pulse compressor to get a total of 80 watt in the infrared. This infrared light is then coupled into a cavity for high harmonic generation. Here we have about 10 kilowatt of power oscillating in the cavity, and we now inject from one side a gas jet, a helium-xenon gas jet for high harmonic generation, and couple the 7th harmonic out of the cavity. And this is the light we then use for spectroscopy, and it generates us on target roughly 1 nanowatt of power per comb mode or comb tooth. So now one question is, can we use this for laser spectroscopy in the clock concept? But a different question is, can we use the same laser also to search for the nuclear transition, right? It is easy if you know where the transition energy is to couple into the nucleus even with low power. But it's a different thing if you don't know where the transition energy is to search for the transition, which may take years in the worst case. However, here I show you based on rough computation, that actually this laser system is not only suitable for the laser irradiation in the clock concept, but the same laser is also suitable to actually search the transition as long as the energy is still unknown. And the reason is that all 10 to the 5 COMP-Ts are used in parallel for the transition search. So for this reason, we have many COMP-Ts, but we are using all of them in parallel, which is like having many lasers, 100,000 lasers that we use in parallel to search for the transition. And now we only have to bridge the comp mode spacing, which is about 77 megahertz, if we want to cover the entire envelope bandwidth of the total comp. And now we have to scan with a certain amount of step sizes, but these step sizes don't need to be narrower than the actual width, the line width of the transition, which is internal conversion broadened. So we have a lifetime of 10 microseconds, and this corresponds to roughly 16 kilohertz of line width. So if we scan this 77 megahertz mode spacing of our frequency comb with a step size of about 16 kilohertz, which corresponds to the line width of the nuclear transition, which is internal conversion broadened, then we would need 4,800 steps roughly. And even if we assume that we are scanning with 1,000 pulses per scan step, which we need because we only expect 0.1 electrons emitted per scan step. So this means we would expect roughly like 100 detected internal conversion electrons per scan step in case of resonance. Then we need 15 minutes to comb the mode spacing. Now, unfortunately, the energy right now is not constrained to cover like the entire uncertainty range with one envelope bandwidth of the comb. So we would need roughly 10 shifts of the comb center to cover the 1 sigma energy uncertainty. So if we do this measurement 10 times, we will need an overall scanning time of 2.5 hours, which is realistic even if you consider some problems. So this is a realistic scenario for actually doing precision search of the nuclear transition. Now let me give you already an application for that. So as soon as the nuclear transition has been found, it is straightforward to develop a nuclear clock, because in this case, we already have a narrowband laser. So we just need to lock our frequency comb to the nuclear transition, and we would have a nuclear clock operational. And the very high sensitivity of a nuclear clock for potential variations of alpha has been predicted. This requires the comparison to an atomic clock, but fortunately, we have a strontium optical lattice clock sitting directly next to us. So for this reason, what we can immediately do is, in case that the transition is found, we could lock our comb to the transition, have a nuclear clock, and could start with comparison, because we would lock our nuclear optical clock to the same frequency comb as the strontium optical lattice clock. So we could compare the frequencies, and by relative frequency drift, we would gain a high sensitivity for potential time variations of fundamental constants. And this brings me to the end of my talk. I give here a short summary and an outlook. So the nuclear clock was proposed first back in 2003 and has been a long-standing objective. A single or multiple ion nuclear clock would offer unprecedented potential for 10 to the minus 19 accuracy. However, an imprecise knowledge of the cerium-229 energy has so far hindered the development of a nuclear clock. Since 2019, a total of 7 new energy values were published, and this new knowledge offers great opportunities for direct laser spectroscopy and a nuclear clock. Today, direct frequency comb spectroscopy is the only way for narrowband excitation of the nucleus. If achieved, an internal conversion nuclear clock could be realized based on existing knowledge, and the experiment is currently in preparation in our lab at JILA. So we strongly hope that the measurements will be able to start in February. So I hope I have convinced you that there are some exciting new prospects for the development of a nuclear clock. Of course, there is a lot of research investigating towards the cerium-229 nuclear clock, around the globe, like, for example, also in Mainz. I don't list all groups here, I have to admit. So this was a slide that I did years ago, and I should probably update this. But this is just how to give you an impression how many groups are actually working in this field. And I would like to thank you for your attention. And within the past 10 years, I've been working with many collaborators. So many people have actually contributed directly or indirectly to this work. And these are just the people I've most recently been working with you. This is my colleague Changkun Sang, who has great knowledge in this laser spectroscopy. So he is actually trying to get our frequency comb under control and is doing great work on this. This is Jun Yi, my current boss, Peter Thielhoff, my former boss, and Benedikt Seiferle, who has proceeded with me this energy determination of the nuclear excited state and has done a great job in the energy determination within the past couple of years. So with this, I would like to thank you for listening.
Thank you very much, Lars, for this nice and very exciting talk. The talk is open for discussion. Yeah, please, Dima.
Thanks so much. This is a super interesting talk. I have a few questions for you. One is, folks like to look for nuclear resonance fluorescence in solids, Eric Hudson and company. What's the status of those experiments? And have they covered the 8 electron volt range where the level is?
So yes, they are able to cover the energy range already now with their laser. So they are, yeah, it's a bit of a head-to-head run. So they are, we are working like in a friendly competition. So the interesting thing, they are using a different laser, which is broadband. So ultimately, this has a great potential because they have a larger energy range that they can cover with a laser, and they have a significant advantage in terms of signal to background ratio because they have a lot higher laser power. In the end, the laser system, they are generating this via 4-wave mixing in a gas, 4-wave mixing scan. So this is pulsed, 5 nanosecond pulse duration, if I remember correctly. And in this way, they generate something like 1 to 10 gigahertz bandwidth of the laser. So their laser system is a great searching machine for the nuclear transition because it's so widely tunable and has so high power. In the end, this is a great experiment for the search. On the other hand, it's a broadband laser spectroscopy, so they would not be able to do this precision spectroscopy in the end and stabilize the laser for the nuclear clock. So it's a bit of a
solid. Is that correct?
Yeah, it's so they are doing different things. So one thing is actually they are investigating crystals, where they are searching for the photonic decay channel. In parallel, they are also doing exactly the same thing as we do. They are irradiating a metal substrate and search for internal conversion electrons.
Mm-hmm. Okay. I also have a little comment. You said that currently these technologies that you are described are the only technologies for CW excitation of this transition, but I would like to point out that here at Mainz, in the group of Professor Jochen Walz, there is a CW laser system developed originally for hydrogen and anti-hydrogen spectroscopy, and it is a CW system for even shorter wavelengths. So one would imagine it's possible to develop a similar system in the future when the transition energy is known to
That's
drive
very
it.
interesting. Yeah, I didn't know about that. Yeah, this is a very exciting thing. No, I didn't know that there are already CW lasers available in this wavelength range for hydrogen.
Only in Mainz.
So this what we are doing here is not CW, right? I mean, we are working with femtosecond laser pulses. So we are not doing CW laser spectroscopy here.
There are a couple of more questions currently, and I just like to point out, that's why I'm interjecting, that I cannot raise my hand, right? I'm as a host, or at least it's not, I'm not aware of it, right? So if anyone knows how I can raise my hand.
On the video, Armin. Yeah, like that.
I raise my hand. Okay, so there, maybe we start with Hendrik and then Christoph and Ferdinand. And after Ferdinand, I have a question too.
Okay, thanks, Arne. Yeah, hey Lars, thanks for the excellent overview.
Hi.
Really liked it. So there are several people such as Eugene Takalia and Eckhard Pike who have proposed the electron bridge process to excite the upper clock state. Their proposals were based on the older incorrect energies for the clock transition. However, by going to more highly charged ions, we could expect to find some electronic structure that's still suitable to drive the electron bridge process. You didn't mention this at all in your talk, so is there any reason you do not believe in this method?
No, absolutely not. So I think this is a highly exciting opportunity. I think it's complicated. So to put it so, you need to know a lot knowledge about also the atomic structure, and you need to actually successfully investigate the electronic bridge excitation scheme. But I think it's a very exciting thing, and it's absolutely doable. I just didn't mention it here because I wanted to focus on our recent work. So no, but there is no particular reason for not mentioning this here.
Sure. Thank you so much.
Yeah, Lars, thank you for the very nice overview to bring us up to date on all these various developments. I have a question concerning your slide where you showed the low-hanging fruit, and I am wondering if it is really hanging so low, because in the end, what you describe is the process that you're looking for. You irradiate the sample with your laser, you look for the IC electrons, and you gave an estimated background rate of like 1 order of magnitude less compared to your signal that you're looking for, and mentioned that this is due to the radioactivity of the target. But if you irradiate a sample with a laser, probably you will also stimulate some other processes in the shell that will emit electrons. And last but not least, you also probably will do eventually some damage to your sample. So do you have any experience what happens with a sample if you use that type of laser technology for an extended time?
Yes, thank you, Christoph, for raising these questions. So yeah, we did preparatory tests on that because, of course, this is a concern. Not so much the target damage, because the power that we are using in our approach is relatively low. Like with this 1 nanowatt, you're 8 orders of magnitude below the ablation threshold. So we do not expect to do any damage to our target with this laser system. However, actually these delayed electrons or even photoelectrons that may occur delayed was a big concern when we started this approach. But we have now done significant tests on that. And it turns out that all like delayed electrons that are emitted from the target are fading away within sub-microsecond time scale. So the lifetime of this metastable state is long enough to clearly distinguish between any like delayed photoelectrons or background electrons that are originating from the laser spectroscopy itself. So after like 1 microsecond, we really have a flat spectrum where we are very sensitive to the Intel conversion decay. And this is based on experimental investigation.
Okay, perfect. Thank you.
Yeah, hello. This is Ferdinand Schmidt-Kahle. My question was exactly Christoph Döhlmann's question. So thank you for the answer. Thank you for the talk.
Ah, great. So it's my turn now. But I'm sure that there are other questions. So you, I mean, the audience could just, I really like the raising hands. At least it orders it somehow. So my question is twofold. Maybe one is, like what makes thorium so special, right? I mean, you mentioned it's like just one in the world, and that we know about. And I'm not a nuclear physicist, so probably everybody from the KPH knows this, but I don't. So maybe you can illustrate a bit why thorium is so special, and whether there are like other searches for other candidates of isomeric states that are maybe even at a bit of a higher energy, or is there a systematic search for those new candidates, for clock candidates?
Yeah, thank you.
It's
That's
one
an
question.
interesting question. So what makes thorium-229 special is really, and most importantly, the low energy. So this metastable state has like 10 electron volt energy, and this is 3 orders of magnitude away from the next one. This is already like above.
Okay, so that is the question. Why is it so low?
Oh, I see. Why is it so low? Yeah, the short answer is it's a coincidence. The long answer is, so it is not possible from theory to predict the energy of nuclear excited states to this accuracy. Yeah, it's not possible. It's not possible to explain theoretically from the theoretical point this low excitation energy. From this standpoint, it's really an abnormal coincidence. However, interestingly, it is known that there are low energy nuclear excited states in the 229 isotones. So if there is a certain region of nuclei where you can expect low nuclear excitations, however, even in terms of this low excitation, so if you talk about low energy nuclear excitations, you're in this region, like around 10 kilo electron volts, you say, oh, this is a low energy nuclear excited state. And there are certain ranges where you expect, for nuclear structure reasons, nuclear excited states of such low energy. However, to really go down this additional 3 orders of magnitude is not theoretically explained today.
Cool. And then thanks for the answer. And maybe, yeah, I don't want to be controversial here, and I really like the thorium developments. It's really exciting and everything, but it's also, I find, a bit of a weak argument that you basically say, okay, we go for a nuclear clock, and then we give it optical properties, right? So like we take the one that is at 10 electron volts, and you do that because you do not have lasers at higher frequencies, right? So you could also go, for example, for the uranium-235 isomer, and you have like an even faster ticking clock, or you can go to maybe like the low kilo electron volts. And the question there is, are there any light sources that could probe those with the required accuracy? Or, I mean, I mostly have the gamma factory still in my head that Dima was sharing a workshop on last week. So what about just going full nuclear into a range where there are actually more transitions that you can probe?
Yeah, it's an interesting question. Yeah, ideally we would want that. So this uranium-235 has also been discussed as a potential use for a nuclear clock. The problem is that it has an extraordinary long radiative lifetime. So you need, even if you had a laser available in this energy, you would need extraordinary high laser power to actually excite this efficiently. For this reason, this is practically ruled out. Yeah, you could theoretically go to other low energy nuclear excited states in the range of like 10 keV. There are free electron lasers available in this energy range, and the Mössbauer spectroscopy line of iron has already been successfully excited by this method. The problem is here that these are laser sources that are typically not narrowband. And in particular, if we are talking about the development of a clock, of an optical clock, We want the laser source to be ultra narrowband, like ideally in the millihertz spectral range. And to the best of my knowledge, no such light sources are available. There are light sources available that cover these transitions in terms of energy, but not in terms of spectral width. However, also this can be subject to future developments. So I don't want to principally exclude that within decades of research, laser sources will be available that are narrowband enough to actually use this other transitions for nuclear clocks. This would be very exciting. Yeah.
Thank you. I have a question, Lars, concerning the lifetime for the thorium ion, which you given here as 1 × 10⁻⁴ seconds. This has been probably theoretically predicted to be like that, and there are no measurements yet.
Yes, that's correct. So the radiative lifetime is a value that has been predicted from theory. The paper is the paper 2 here. The latest one is from Nikolai Minkov and Adriana Palfi. I think the theory is pretty well under control by now. So I personally trust this value.
Okay, but my question concerns the experiment. You should have been able to extract thorium in 1+, for instance, from the gas cell and so on. Have there any activities concerning the lifetime of the thorium in the 1+ state, for instance? Yes.
This is something that is currently, or an experiment that is currently prepared at LMU Munich in the group of Peter Tirov. So far, the determination of the lifetime was limited by the achievable storage time of the thorium-229 ions in a Paul trap. And for this reason, what is currently developed is a cryogenic Paul trap that will hopefully allow to store the thorium-229 ions to a sufficiently long time to actually see the isomeric decay proceed over time. So yeah, it was just technologically constrained, but this will most certainly be solved within the next couple of years, and then we can access the lifetime, the isomeric lifetime in different charge states, which will probably be very close to the real radiative lifetime of the isomeric state.
So you expect different lifetimes, right, for the different charge states?
Right. Well, the radiative lifetime is a fixed value, but the real lifetime depends then on how many other decay channels you have involved, right? So you have the internal conversion, which is a super strong lifetime, but this super strong internal decay channel, but this will in thorium 3+, for example, be absolutely energetically forbidden. But still there might be electronic bridge effects that can still lead to a reduction of the isomeric lifetime compared to the pure radiative lifetime.
Thank you.
So Henrik actually dug out an explanation for the separation of the isomeric state, or the small energy, if you want. He asked you to comment on something, but I'm not sure what the comment should be about. So,
well, you don't have to directly comment on it. It seems more like a theory sort of knowledge. But I don't know if you can read the text. Maybe you do have something to say about it, but don't feel obliged.
I don't know. I can maybe stop the presentation for now. Can I see this somewhere, or?
You have to click the chat box, or
I see the
Alt
chat.
H.
Oh, yo. Yeah, right. I mean, this is this is the internal structural explanation. So you have some you have always for each nuclei you have a Coulomb term, and you have a different term that is caused by the high energy parts of the nucleus, the nuclear coupling parts, and these will always have to be compared to each other. So you will, for each excited state of the nucleus, you will always have some sort of cancellation between Coulomb energy term and the nuclear energy term, which is composed of different high energy nuclear values. However, as far as I understood, the question is why is the energy so low? And there is no explanation why these terms actually cancel. So I would still say it's a pure coincidence that for the thorium-229 isomeric state, these two energy terms almost exactly cancel out.
Maybe they were created for in this way for us to study them. Okay.
Exactly. I mean, this is not how nuclear physics people think, right? If they find something abnormally low, then they call it a problem and try to solve it, right? With potentially additional particles. Okay. Yeah. Are there more questions? Maybe while you think about more questions, I can advertise next week's seminar, which is going to be the last seminar of this year. So you can all dress up with your Nikolaus costume. And it's going to be by Markus Ahn from the University of Vienna about the long road towards interferometric tests of non-standard physics. It's going to be interesting. Are there some last questions?
It seems not to be the case.
But thanks again. This was a really great talk. Thank you.
Thank you. It was my pleasure.
Okay. So I think we can now close the session. There are no further questions.